So thank you very much. I'm happy to be here today, and I'm honored to be able to provide some information to you on IPC activities in this area, and we'll talk specifically about two IPC standards that are relevant to reliability. So this is me. I just celebrated our 46th anniversary with IPC. And they gave you my background information. This is my contact information if you're interested in connecting after the meeting. From the association standpoint, the areas in blue are where we currently have staff positioned around the globe. We have over 200 staff members. I was employee number 9. And we are working to support the global electronics manufacturing industry. We have over 3,200 member companies that are part of IPC, now branded as the Global Electronics Association, and we work to support a $3 trillion industry. Now, they asked me to set the stage a little bit, so I have a question. How many people in this room consider themselves a reliability expert? Don't be shy. I'm not one of them, so I'm not putting my hand up. Okay, so we all have things to learn about reliability. And I'm going to share what our association has done, because we have over 2,000 subject matter experts that participate in our standards activities. And so it's not my expertise, it's their expertise on what they want, what they're able to contribute and share for future generations. And so why is this event important? And so, what's the cost of reliability failures? Yes, there is cost involved in testing and trying to prove out that the product is reliable. But as you start to go from the initiation of the design and into potential opportunities for reworking defective products, maybe do warranty recalls, and the price goes up significantly as you go up that curve of shipping product to the marketplace. And so if you look at the potential for failure and what has happened, there are some spectacular failures of reliability in the field, and I converted these to Thai baht. $210 billion was what they estimated the Samsung Galaxy Note, the fire on the phones. Microsoft Xbox, 32 billion Thai baht. The Takata airbag, 630 billion Thai baht. Intel Pentium recall, 15 billion. Toyota's unintended acceleration, 63 to 126 billion. And then it's estimated that if a cloud server is down, that the costs are between 9.5 and 32 million baht per hour. That can buy a lot of pad krapao musap. So, and it's getting more challenging. The products that are coming out today continue to push the performance, and the margin of safety continues to be reduced or squeezed. And so you have compressed development cycles. People want their products, companies want their products to market faster. The amount of energy and power going into equipment, jumping to 1,000 watts per a GPU chip, up to 10,000 watts for an AI server board. The devices continue to shrink. EV power is increasing, charging requirements increasing. And so these are the challenges that we have with trying to deal with these stresses. If you're using a standard qualification test that you've used for years, you're continuing to work and squeeze the gap between what you're able to test prior to going to market to what you may see in the field. And so the tests that were used in the past may no longer be adequate. And then as you continue to advance technologies, you see new challenges that may come to bear. So the traditional qualification gap, products are typically qualified to a specification that the customer gives, or an IPC standard, a regulatory requirement, but it doesn't give you the information. It gives you the information that the product will survive will it survive the expected environment? It doesn't answer what happens if it goes beyond that environment. What if there's a spike somewhere? What happens? Is there a destruct boundary? And so you're not seeing all the potential stresses that might be seen in the environment. It's giving you pass-fail compliance testing. And so qualification confirms compliance to a document, a standard, and other alternatives are needed to truly understand what the limits of the electronics hardware are. So the standards indicate that a better approach or a reliability approach falls in this flow. And we'll talk more about this as we go through the presentation. With DFMEA, a cross-functional activity between the design group, the manufacturing group, quality and test, as well as the customer, intended to determine what potential failures might be taking place. We'll talk about HALT, and we'll have a lot of discussion on HALT today in today's session. Qualification, we've talked a little bit about, intended to meet the specs, and then HASS. So I'll turn on to talk about how these are reflected in the IPC standards. There are two standards that we're going to talk about today. One is 9701, which was specifically created to gather data on solder joints. And we need to talk about and highlight the time frames that these standards were created in, because that's important. And the 9592, which is a unique standard in IPC's history, which I think is important and would be a good model as we're trying to move forward more quickly. So let's start out with the 9701. This is to look specifically at the surface mount solder joints. Now, this was created by a committee of reliability experts. That's why I asked you to raise your hand, because we need more reliability experts. My fear, when I was putting this presentation together, I got worried. Not that I would be nervous in front of the audience. Where are the reliability experts? The reliability experts that worked on some of these things, some of them have passed away. Some of them have retired. And it's important, if you're working in the reliability area, you're needed for the future. And so, but the main points and the basic points are still relevant to be able to be a basis for future use. So the 9701 was created because the industry was going from lead-bearing solder, tin lead, to lead-free. And the industry did not have confidence that the data existed to properly determine reliability of lead-free solders. And so these standards, you can see, was created in 2002, was the origination. They went through an A revision to add in lead-free solders, alloys in 2006. And the goal was to be able to create a process by which data could be collected and shared to have for high-rel markets that might be pushed by this change. So The focus of the 9701 was lead surface mount solder joints. The objective was to permit analytical prediction of reliability based on an industry database and provide standardized test methods. So it wasn't a product standard. This is a test vehicle standard to gather data that can be used for companies when they're doing their models or their own evaluation. And they didn't use HALT, the highly accelerated life testing. They considered something, they considered it, I would say, ALT. It was accelerated life testing, and in the standard it said that the goal on this one was to come up with stresses that were about 10 to 20 times. It would shorten the life by 10 to 20 times compared to 100 to 500 times, which you might see as far as the stresses that go into a HALT test. Now, what kind of conditions are you faced with? And so they, what they did was, now this is, there's lots of text on this, but this is a table from IPC SM785. The objective of this was to collect a reference point for various industry segments, various hardwares, the cycles, the temperature extremes that are seen in these environments, the number of cycles that this hardware would see in its lifetime. So this is a useful reference source when somebody's coming to say, I'm going to be putting a product into a military aircraft. What should I be considering as my conditions when I'm doing an evaluation for reliability? So this is a useful reference table that is included in the 9701. Okay, and so now you would take that reference table, and then the committee came up and said, okay, how would we recommend that we would evaluate these solder joints? What type of testing? And so in this table, they have a series of cycling requirements, 1 through 5. They have a number of cycles requirements, A through E. And they indicate the timing at dwell, which is important to have a standardized dwell. If you're going to try and compare data from multiple companies, you need companies to be using similar conditions. And so this table was captured to say, here are 5 cycle levels, here are the temperature extremes, here is the dwell, here's the temperature rise, here's how many samples you should use to gather this data. And so this one was important. So, but if you look then, how do you decide, or who decides? Well, in reality, it's the customer that's going to talk about what they want to see in their product. But if I looked at this and said, okay, I know I have a military aircraft, I know that it's going from -55 to 125. In the table 4.1, I look at that and say, okay, that puts me at TC4, test condition 4, -55 to 125. From then the number of cycles, it recommends 1,000 cycles. And so this is the data that someone would want to recommend for this particular market segment. And so that's how this one was created. And so this standard has been in place since 2008 and used successfully to gather data on tin lead and lead-free solder. So I'm now going to switch gears to the 9592 standard. This is a product standard, not specifically a reliability standard. However, all the tests in there focus on reliability for these products. So if you're not making power conversion devices and you're still interested in how an industry segment approaches reliability, this is a really useful one to look at. And let's give a little bit of history, because this is a unique standard. We didn't get a group of reliability experts to create this standard. We had an industry group come to IPC. So these logos came to IPC and said, we have a problem. We want to reduce warranty repairs, or the cost of warranty repairs that our products are seeing in the field. And this is specifically for power conversion, power supplies, power conversion devices. We want to reduce the warranty, the frequency of warranty, and we would like to work together as a group of companies that are buying power supplies from industry to try and help the industry give us more reliable products. And so they all had, every one of these companies had their own internal standard that they were using. And they said, you know, if we wanted to help the industry to improve, if they were all working to one standard, it would reduce their cost because they only had one document to work to, and then we could help focus on improving that from there. And so this was the objective. This standard was created in 2010, went through one revision, and I found out, because this is not our most popular standard, but we had a discussion with a power supply organization, and they use this standard all the time. It has been really, there's been a major impact of this. And why is this important? Well, there's 40 to 50 million of these type of things, types of products produced annually, and that's probably a conservative number. And so there's significant potential costs that are in there. The types of products, there's a couple categories. One would be the types of power supplies that you use for your laptops and such, but it also then goes up to the types of products that would be in servers and the cloud servers and various infrastructure devices. So it covers all power supplies. So let's then, they spent time in the standard then talking about how you might approach this. And they spent more time on the design evaluation, DFMEA, Design, Failure, Mode, and Effects Analysis. And so how many companies are doing DFMEA? Okay. So the purpose of the DFMEA is a brainstorming process followed by data analysis once you have data. So you actually start this before you build a product. You have a product design, you have a group that gets together and says, where are the most likely failures to be seen? Where do we expect that this product might fail? What's the possibility? And if a failure occurs, how severe would it be? And so the objective is to try and gather that information even before you go to manufacturing. We'll talk about HALT and QUAL and HASS later on. So with the DFMEA, the objective is to try and prevent failures by brainstorming, considering your design, looking for weaknesses in the design that might end up being a reliability failure. So you evaluate the impact of these weaknesses and the risk associated. Is it going to be well, I have to reboot, or is it going to burn the house down? These are the kind of categories that you put in your analysis. You prioritize how you would mitigate these if it truly comes out in some of your testing that these are challenges, and it helps you improve the design. So DFMEA should be done sorry. DFMEA should be done at the product concept stage before you fix the design and before you build your first prototype. And then as you gather data through your actual testing, you'll be able to make modifications. And if you have any field failures, hopefully not, but you're able to then have this group work on mitigation. So then, and what you'll find in a number of presentations today, the highly accelerated life test. So HALT is where you work to break something. You are going to try and make your product fail. This is your objective. You are looking for weaknesses. And so you're going to throw anything you can think of from your DFMEA into your product to try and make it fail, to find the weakness so that it doesn't, so your customer is not finding the weakness, you find it and fix it. And so the objective is that you're going to shake, bake, heat, and everything to try and cause a failure. And so this is what the balance of this standard is intended to do. So there are a variety of different types of ovens or chambers that can do this. Typically, they have heating, cooling, they have vibration, they have power cycling, and so you're using these to cause the stresses that you're going to hopefully find the weaknesses in your product. So the objective of this stresses is to identify where things break. What is the lower destruct limit? What is the upper destruct limit? And where's your operating margins? And so, so that when it's going to the field, you have your specs, which the consumer would normally run that product in, and then understand what are the upper and lower limits. And so the objective of this is to identify where these barriers or where these limits are. So you'll see these charts in many of the presentations, and the process seems to be very similar. These are intended to take the product to failure, so you'll have a temperature, low temperature product, low temperature, normally dropping 10 degrees C with a 10-minute dwell, and you're going to take this until you either hit the limit of your chamber or until the product fails. And this then gets repeated for same for the high temperature, the 10 degrees up over time, again, until you see failure. Once you have those, you can run through a version of thermal cycling, differential conditions, 10 minutes. They made in the standard, they have different requirements depending on whether it's for lead-free, which is a longer dwell time, or tin lead solder. And so you run through a thermal cycling test, at least 30 cycles, or minimum of 30 cycles, you want to take it to failure. So in this case, you're not simulating life, but rather the weakness, discovery of weaknesses. Vibration, the requirements for stepping of higher levels, 10% of the chamber capability or the table capability to failure, and very similar. If you go to the voltage, 1 volt change, and you're checking both voltage in and power out over time, seeking where you might see failures. When all that's done, you combine everything. So you have the heating cycles, you have the vibration, you have the power all going on, and the objective is then to have this comprehensive set of information that gives you the information as to where your product limits are. What are the destruct limits? So some of the common things that are seen in there would be potential solder joint fatigue, connector fretting, problems with the PCB CTE mismatch, even some software challenges with firmware instability. And the standard references, some of the mistakes are if you're not looking at this let's put it this way. If your product is only changing by a few percent, you come up with a new rev. Well, why don't we skip HALT this time? And maybe that works for a period of time, but if you're trying to take what the product life failure was for your last product, you're treating HALT as a you're depending on data from a set that may not be the same type of product. So the objective is to look at this with the intent of determining the true destruct limits for the hardware that you're providing. So after you've gathered your information from your destruct testing, switching to the qualification. The qualification, as I mentioned earlier, is going to be done to either a customer spec or an industry spec. It's not intended to, or generally is never looked to qualify to destruct limits. And then you will identify what you might use for burn-in or highly accelerated stress testing. Just to, for HASS testing, you're trying to find manufacturing defects. Is there an only partially soldered solder joint? Something that be detecting your manufacturing escapes. And so after you're out of HALT, you then go into your qual and your HASS. And you end up with a diagram that looks like this. Your customer's requirements, the originating limits. You have your product operating limits, the upper and lower. Your HALT has given you a destruct limit, so you know that the end point. And your HASS limit is going to be beyond the operating limits, but less than, beyond the customer operating limits, but beyond, between the product operating limits. So this is a screening test just to see if there is a manufacturing defect. There are other tests, so these are the reliability tests that are in this standard for power conversion devices. There are a number of other what you would consider to be reliability tests that are not as involved as the HALT testing. Drop, there's many where you're going to how high and how much weight. Shock corrosion, but all of these tests are included in the 9592. So the takeaways on the HALT and HASS qualification is looking at your conformance to your customer requirements. HALT is beating the product up with the intent of finding destruct limits and producing increasing the robustness of your hardware. HASS HASS looks at manufacturing failures, and your margin is what you have for your field reliability. So we have other standards that address reliability. Many of these are fairly old. We work with other associations in the creation of these. Just walk through these briefly. And by the way, I can provide these slides to THPCA so that they can share them with the attendees. The SM785, which I referenced the table earlier, look at the date on this, 1992, has not been updated since. Again, looking for additional reliability experts to participate. Design for reliability for surface mount technology, 279, also from the 90s. Some of the standards looking at component reliability issues, particularly in moisture sensitivity. We work with JEDEC on these. These are joint standards. 020 for plastic components, 035 for non-hermetic, this is for microscopy, acoustic microscopy testing, and 075 for non-IC components. We've also worked with JEDEC for some test methods to try and push to determine what the limits of certain technologies are. This was specifically looking for surface mount solder ball attachment, primarily in BGAs, and trying to put it through some stresses to see how the attachment of the component to the board are. And so that test procedure puts it through. It then gives you an idea of how you should be, where this should be tested in your manufacturing operations. So if you're just trying to determine what stresses take place in the manufacturing process, the intent is to determine what happens to BGA balls during the manufacturing process. If you're doing all this deflection of the board during assembly and such, is that stressing the joints that may end up being a field problem down the line? The solder drop test, very challenging, but very important. This is something that, of course, all your consumer products do. Identified the test procedure for doing that, so companies are doing it in a similar fashion. And this one was looking at some of the strain rates of SMT packages to boards during assembly, because there was concern of cracking at the copper pad layer. So I want to highlight some of the other activities that we have going on. We, on March 30th, here at Bangkok, we're going to have a session on best practices of PCB design and quality performance evaluation of PCBs. And we are starting an IPC standards activity in Thailand. This will be our first standards committee meeting. This will take place, the standards meeting will take place at 1:15 on March 30th at Hotel Siam Mandarina. And so if you're interested in that, we are looking to be able to engage Thailand in IPC's global standardization activity. We would encourage you to consider sending someone to this event. From an event standpoint, we have been running the Integrated Electronics Manufacturing and Interconnections, IEMI. We've had 4 years so far. The 5th edition of this will be held in Malaysia, not very far away, for Thailand to attend. This will be 2 days, one in KL and one in Penang. The focus will be on aerospace, automotive, and artificial intelligence. We have staff members in Thailand to help you with your issues or your questions on IPC activities. Raj Tiwari is our country manager. Raj is sitting in the front row. And Jib is our manager of member relations, and Kunshiri Khan is our instructor. So we have our staff members that are here. If you're interested in talking about anything IPC or Global Electronics Association, we would encourage you to reach out to these individuals that they can help your company. That completes my presentation. Thank you very much. And again, thanks for the opportunity to share this information. I hope you found some of it useful. Khop khun krap.